Okay, let's do the Chapter 9 review. I'm on page 286. Number 1, define the following terms. A solution, A, is a homogeneous mixture of two or more substances. B, a solute is the substance that's dissolved in the solution, or it's the dissolvee. C, the solvent is the substance that is dissolving the solute, so it's the dissolver. D, solubility is the amount of solute that can be dissolved in a specific amount of solvent. E, a saturated solution is one that is holding the maximum amount of solute dissolved in it. C, precipitate is a solid that comes out of a liquid solution. And G, concentration is the amount of substance in a defined volume. Number 2, bronze is a homogeneous mixture of mostly copper with small amounts of another metal, such as tin. Identify the solute and the solvent. Well, the one that's being dissolved is the solute, so those would be the other metals, such as the tin, and the one that is doing the dissolving is the solvent, so that would be the copper. What do we call solutions made from a metal and other solids? Those are called alloys. Number 3, which will conduct electricity? A solution of water and ammonium sulfide, or a solution of water and glucose is what that looks like. It will be the ammonium sulfide, NH4 to the 2S, because that is an ionic compound. Number 4, if you are able to look at a solution of potassium phosphate and see all the molecules and ions, what specific molecules and ions would you see? Now, remember, this is potassium phosphate and it's aqueous. The AQ means aqueous, so it means it's in a solution in water. And so the molecules that you would see would be, or the ions, you would see molecules of water, you would see ions of potassium, remember they're a positive 1, and you'd see ions of phosphate, they're a PO4 minus 3. So those are the molecules and ions that you would see, which, and then it says, of course, of those, which make up most of the solution, that would be water, because that's most of the solution, and which make up the least amount of the solution, that would be the phosphate ion, because there's 3 times as many potassium ions as there are to any of the phosphate ions. Okay, number 5. The illustration on the left attempts to show how a polar covalent molecule dissolves in water. What is wrong with it? Well, if you'll look at that, it has the water molecules are oriented incorrectly. The water molecules are going to be, the hydrogen ends are going to be towards the negative, and the oxygen end is going to be towards the positive. What am I talking about here? This end of the water molecule is more positive, so it's going to be oriented toward the negative end of the other molecule. This end of the water molecule is more negative, so it's going to be oriented to the positive end of the other molecule. And so that's what's wrong with the picture, is the water molecules are not oriented correctly. Number 6, an aqueous solution contains 3 sulfate ions for every 2 aluminum ions. What is the solute? Okay, so it's an aqueous solution, 3 sulfates to every 2 aluminums. Three sulfates to every 2 aluminums, and it is aqueous, because it actually said there an aqueous solution. Number 7. You are making a solution. I guess you didn't have to have aqueous, but that's the solute. Let's see, number 7. You are making a solution by dissolving solid silver nitrate in water. What can you do with temperature to increase the solubility of the silver nitrate? If you increase the temperature, it will increase the solubility because there'll be more motion in the molecules. And so increase the temperature. Number 8, you are trying to dissolve as much of a gas into water as you can possibly dissolve. How should you adjust the pressure and temperature? You should increase the pressure and decrease the temperature. Because remember, when you increase the temperature of a gas, it starts busting out and moving around faster, so it's harder to get it into solution. So you want to decrease the temperature, but you increase the pressure because then you're pushing it down into the solute, the solvent, and it has more of a chance to dissolve. So the answer would be increase the pressure, decrease the temperature. Number 9, a solution of solid solute is saturated. Wow, a lot of S's there. Alliteration. If the temperature is lowered, what will happen to the solution? Some of the solid solute will probably precipitate out if you decrease the temperature, because it would decrease its solubility and therefore it would fall out as a precipitant. Number 10, a student performs the following reaction by mixing a solution of manganese chloride with a solution of potassium hydroxide. And so there is the equation. Did a precipitant form when he mixed the solutions? Well, if you look at the phase symbols on the products, you'll notice that the first product is aqueous, but the second product is a solid. So yes, there is a precipitant. And if so, what is the precipitant? It's manganese hydroxide, MnOH with the parentheses 2, because that's the one that is the solid that came out. Number 11, calcium carbonate is insoluble in water. If a solution of calcium nitrate and water is mixed with the solution of potassium carbonate and water, what reaction will occur? So we have a solution of calcium, and you know that's +2, nitrate, that's a -1, so we're going to flip-flop. We have calcium nitrate and water is mixed with a solution, calcium nitrate and water, I'm so sorry, that's aqueous. A solution of calcium nitrate and water is mixed with the solution of potassium carbonate, so that gets the 2, that gets the 1, with water. What reaction will occur? So we're going to end up getting calcium carbonate. That's a +2, that's a -2. And this, we're told, is insoluble in water, so it's going to fall out. And then what's left is the potassium, which is a +1, the nitrate, which is a +1. And so that's going to be a 1-to-1 relationship. And then we have to balance this. We need 2 of this because we have 2 and 2, and then that takes care of our 2 and 2. And so that's the reaction that we would get. Calcium nitrate plus potassium carbonate. Those are both in water, so they're aqueous. We're told that the calcium carbonate is insoluble in water, so it's in the solid form. Oh, I'm sorry. And then this is aqueous, because we're not told that that falls out. Okay, so there you go. Number 12. Let's ditch this because we don't need it. A solution is made by dissolving 100 grams of lithium sulfate in enough water to make 325 mils of solution. What is the concentration in moles per liter? So in the molarity, that's what we're looking for. We have 100 grams of lithium sulfate, and we have 325.0 milliliters of solution. Okay, we're trying to find the molarity, which is always in moles per liter. We've got to get this into moles and this into liters. Okay, the lithium, when you add this up, is 109.94. And so that's going to give you, in 4 significant figures, 0.9096 moles. And then this, I'm going to show you this time, and then I'm going to assume you're going to be able to do this. We actually just moved the decimal place back 3 to get liters. And the reason is because the milliliters, there's 1,000 milliliters for every liter, and that means 0.3250 liters. We just moved this decimal place back 3. Remember, that's a significant figure, so you have to keep it in there. Now, to find your molarity, which is a large M, you have moles per liter, and you have 4 significant figures both places, so you end up getting 2.799 molarity, moles per liter, big M, not a little m, big N, and that's of the lithium sulfate. That's its concentration. Number 13, you want to make 225 mils of 4.5 molar solution of sodium hydroxide. How many grams of sodium hydroxide will you need? Well, we know that molarity equals moles per liter. And we're given here the amount of liters as, okay, and so if we want to find the grams, we're going to have to find the moles, aren't we? So let's solve for moles. Moles equals the molarity times the liters, right? The molarity we're given here is 4.5 molar, which is moles per liter. I'm going to write that here so you can see it. Moles per liter times, we are given 225 mils, so I'm going to make that liters, 2250 liters. And so that's going to give you the number of moles. So when you multiply that out, you end up getting 1.0, because you have to have 2 significant figures, moles of sodium hydroxide. Now once you have that, you can, well, 1.0 moles of sodium hydroxide, it's 1 mole. So you just go and you add up sodium, the mass of sodium, which is 22.99 grams, oxygen, which is 16.00 grams, and hydrogen, which is 1.01 grams. And so that's going to give you, believe it or not, 40 grams. But you have to have 40 grams in 2 significant figures, because if you did this, the moles of sodium hydroxide, the grams of sodium hydroxide, and you put you have to have 2 significant figures. So you need to show this way, or you could write it this way. But make sure that you watch your significant figures there, okay? But see, I could look at that. 1 mole I know is going to be that, but you had to involve the amount of significant figures. That was the tricky part. Let's go to number 14. A chemist wants to make cobalt hydroxide according to the following reaction. If the student uses 167.4 mils of that 1.39 molar solution of sodium hydroxide and excess cobalt chloride, how many grams of cobalt hydroxide will be formed? I know it sounds like you want to hyperventilate, but it's okay. Don't hyperventilate. You can do this. You're going to take it one little step at a time. That's how we climb the mountain. One little step at a time. And so here, the important information starts with the sodium hydroxide and the cobalt hydroxide. We are given, the student uses 167 mils of 1.39 molar solution of sodium hydroxide. So we have a 1.39 molar solution, and we are using, I'm going to convert the 167.4 mils into liters, because this is in liters. So 0.16 0.74 liters. Good, right number of significant figures, just checking. And we want to know how many grams of this is formed. Everybody sees how you put it in. So we're going to start where there's no question mark, drive to where there is a question mark. We know to get from here to here, we have to have moles. Where's the moles hiding? It's hiding right here, isn't it? Right? So let's start there. 1.39 moles per liter of sodium hydroxide. Now we want moles of sodium hydroxide. And we have how many liters are being used. So we are going to multiply this by the number of liters that we're using. And that's going to make my liters cancel, isn't it? And so we'll have 3 significant figures in the answer. And so the answer is going to be 0.233 moles of sodium hydroxide. I know, this is like the only place that you don't take this and put it here. Because we're trying to get to moles, and we already have moles per liter. But we know how many liters we have, so we're going to multiply it by the liters to get rid of that. And that's going to leave us with our moles. Now, once we have the moles, now we can go across the mole bridge or the mole tunnel, however you want to look at it. So I'm going to ditch that. And I'm going to make this moles of sodium hydroxide to moles of cobalt hydroxide. And there's 1 to 2, so 1 to 2. And so, oh, and then we're going to grams. So let's not make a step in between. We'll just go like this. And we go moles of cobalt hydroxide to grams of cobalt hydroxide. 1 mole of that. And that is 92.95 grams. Okay, now this will leave, we'll be left with that. We have 3 significant figures. So our answer has to be in 3 significant figures, so it's going to be 10.9 grams of cobalt hydroxide. The only thing that's really new is this part right here. And you're just going to find the moles from the molarity times the volume in liters. And that will give you the moles. And then once you get to the moles, you do the same old thing you've been doing all along. Number 15, a chemist wants to make 150 grams of barium carbonate using the following reaction. That if she has an excess of potassium carbonate, what volume of 2.56 molar solution of barium nitrate will she need to use? Okay, and once again, that's all like, oh! So just start writing it into the equation. So we have barium nitrate plus, let's see, what's the other thing we need to have? Barium nitrate. Oh, barium carbonate, which is that first guy over here, isn't it? There we go. Okay, the chemist wants to make 150 grams of this. Good. She has excess of this. What volume? So we are looking for the liters. I'm going to put it up top so it's not in my way. What volume, that's what we're looking for, of a 2.56 molar, which is moles per liter, I'm just going to show you, will she have to use? Okay, so there's a question mark over there. So I'm going to start over here and drive that way. So I'm going to go here and I'm going to go 150.0 grams of barium carbonate times line, grams of barium carbonate, moles of barium carbonate. 1 mole of that we'll figure out in a minute. We're going across the mole bridge. So, and actually, this is a 1-to-1 relationship. So I'm just going to put 1 mole to 1 mole and save myself a little writing. But you see there's a 1-to-1 relationship. But this one now, we've gone to that one over there, barium nitrate. So moles of barium nitrate. There we go. Okay, there's our moles. Once we have our moles, then we come back over here. We're trying to find the liters, right? And so yeah, that's what I would do. 0.7601 moles of that times line. We want to get rid of moles, and we want to get to liters, don't we? So I'm going to flip this. There's my moles per liter. I've flipped it. And that way it cancels, and I will be left with the amount of liters, which in this case is 0.297 liters. Now, he shows you in the text why this works. Literally, you can just, when you get to this part, this is your moles per liter. Out of this, I have just flipped it because there's my moles per liter. And then the moles cancel, and you're left with the amount of liters of this that you needed. Number 16. Of the two concentration units you learned in this chapter, which is more like a ratio of the amount of solute to the amount of solvent? And that would be the molality. Because remember, the molality is the moles of solute divided by the kilograms of solvent. So that would make it more like a ratio of the amounts of solute to the amount of solvent. Number 17, you make a solution by mixing 67.8 grams of potassium chloride and 450 grams of water. What is the molality of the solution? Well, remember, I just said molality, which is little m, equals the moles of the solute divided by the kilograms of the solvent. And so with the information that was given to us here, we have 67.8 grams of potassium chloride, which is going to be the solute. And so we're going to take that to moles. So we're going to go grams of potassium chloride, moles of potassium chloride. 1 mole is 74.5 grams, which equals 0.909 moles. And then the kilograms of water, we're given 450 grams of water. And just like taking milliliters to liters, I'm going to show you this once and then I won't show you again because you're just going to move this back 3 times. To have a gram here and a kilogram here, it's 10 to the third, so that is just going to bring your decimal place back. So now to find the molality, you're just going to take the moles of solute per kilograms of solvent, which in this case is water, and there's 4 significant figures in both places. So let's see. It's, excuse me, 3 significant figures. 3 significant figures. Shame on me. So that's going to give us 2.02 molal. Make it look different than your molarity so that you can tell the difference, which one you're dealing with. Number 18, a chemist makes a 2.34 molal solution by mixing 23.1 grams of magnesium chloride in water. How many kilograms of water are used? So once again, we have the molality equals the moles of solute over kilograms of solvent. And in this case, we are looking for this. So if we solve, we are going to get kilograms of solvent equals the moles of solute divided by the molality. And I just solved for this. Because that's what they'd asked for. So the molality is given to us as 2.34 molal. And we are given 23.1 grams of magnesium chloride. So we are just going to find the moles of that. Let's see, magnesium chloride, 95.21, which is going to give us three significant figures, 0.243 moles of magnesium chloride. So 0.243 moles. And when you do that, that is going to give us 0.104 kilograms of water. Three significant figures. You have to know what molality is and then just work your way through it. And it's just algebra at that point, isn't it? Number 19, solutions are made from water in the following solutes. If the molalities of the solutions are all the same, which will have the lowest freezing point? Well, here we are actually using the change in temperature, or the freezing point depression, equals negative I KF molality. And so I is what you're playing with here. So look at these and determine which one has the highest I, because whichever one has the highest I, or made up of the most ions, will depress the freezing point the most. The first, magnesium nitrate, is made up of one magnesium and two nitrates, so there's three ions represented here. The next one is made up of three ions also. One of those, this should be up in here so you're not confused. One of those and two of these, that's also three ions. Sodium chloride is just made up of two ions, 1, 2. NH3 is actually not made up of ions at all. NH for ammonium carbonate is made up of three ions, 1, 2, 3. Aluminum chloride, I'll come up here now. This one's made up of 1, 2, 3, 4. There's three of these and one of these, that's 4. So this one is going to be the one that will depress the point the most, because when you put 4 into here with the other stuff, then that's going to drive it down the farthest. Number 20. What is the freezing point of a solution made by mixing? And you've got the grams of sodium chloride, 250 grams of water. And so here we're using the freezing point depression. So let's go ahead and do that. We just had this up here. Guess I should have left it. Negative I KF mole. And we want to know what is the freezing point. So we're looking for the freezing point depression. We're putting in sodium chloride, so there are two ions, so we're going to go -2. The KF is 1.86 degrees Celsius per mole. How do I know that? Because it's given right there. And so the only thing that's left is the molality. We've got to come up with that. Well, the molality we know is the moles of the solvent over the kilograms of the solute. I got that backwards. I'm so sorry. I'm looking at that going, It's the moles of the solute over the kilograms of the solvent. There we go. Now I've got it. Now how do we find that? Well, we are given the grams. We are given 32.0 grams of sodium chloride. So we go times line, grams of sodium chloride, moles of sodium chloride. 1 mole of that, you add those up, excuse me, and it's going to be 58.44, which is going to give you, in three significant figures, 0.548 moles of sodium chloride. So now we can come up here and go 0.548 moles. And we need the kilograms, where we're told that we have 250 grams of water. So that's move the decimal place back by 3 kilograms of water. And so that's going to give us 2.19, 3 significant figures, mole. So now I can come up here and plug that in. So when I do the math, it ends up giving me a negative, don't forget that's a negative sign, 8.15 degrees Celsius. Now, because it's in water, that's actually my answer, because water freezes at 0. So if you said 0 minus this, or you add a negative, then that would be the freezing point depression. If it was something other than water, you would have to start at the freezing point and then add the freezing point depression, which would be subtracting that number from it. And then that would be how you would get the new temperature. Number 21. A solution made from water and N2H2 has a freezing point of negative 1.5 degrees Celsius. What is the molality of the solution? Well, remember, we know that so now we're looking for molality. So I'm going to solve for that. Okay, and now I'm going to start trying to plug in. I'm told that the change in temperature is negative 1.5 degrees Celsius. I'm told we're using N2H2. I want you to notice this is a nonmetal and a nonmetal. There are no ions involved. So I is negative 1. The Kf is given to us as 1.86 degrees Celsius per mole. And so when you go ahead and just do the math, 2 significant figures, you get 0.81 mole, because the Celsius will leave, and you're left with molality. The 2 negative signs will cancel one another out. And so there's your molality. And that's all he asked for, was what's the molality of the solution. So there it is. Number 22, what is the boiling point of the solution in number 20? Okay, so let's do that. So boiling point, the change in temperature for boiling point is IKB molality. Notice that's positive, and this is now the boiling point constant. And so I'm on 22, right? Okay. Boiling point of the solution in 20. So let's start plugging in. 20, we had sodium chloride. I'm just going to write it up here. So we know that I is 2. We're given the Kb as 0.512 degrees Celsius. We're given the molality. We figured that out up there. The molality of this was 2.19 mole. And so when we do that, 3 significant figures, our answer is 2.24 degrees Celsius. But we're asked, what is the boiling point? And so that is the change in temperature. We know that water boils at 100 degrees Celsius. So we're going to add our 2.24 degrees Celsius to it. And this 100 is supposed to be exact. It has an infinite number of significant figures. So because of that, we take our precision from this one. So that would be our answer, 102.24 degrees Celsius. Don't stop at this point on your test. Your answer will be wrong. Make sure you answer the question he asks you. Very important. Number 23. Oh, we're on the last one. Yay! Snoopy dance, Snoopy dance. Woo-hoo. Okay, number 23. Aren't you excited? I'm excited. The boiling point of ethanol is 78.37 degrees Celsius. If the boiling point of the solution of strontium chloride and ethanol is 80.56 degrees Celsius, what is the molality of the solution? Well, we know that molality, let's see, first off, we know The boiling point is what we're dealing with. Oh, I can write. The boiling point, can you tell I'm getting tired? The boiling point is IKB mole. We are being asked what is the molality of the solution. So I'm going to solve for molality. There we go. Then it says the boiling point of ethanol is 78.37 degrees Celsius. And it says that when we mix these two, the new boiling point is 80.56 degrees Celsius. So first off, that gives us a change in temperature of 2.19 degrees Celsius. So that's the first thing I can put in here, 2.19 degrees Celsius. Now, the next thing is we need to figure out I. We are dealing with if the boiling point of the solution of strontium chloride. So that is, I'm going to just write it here for you. I is going to be 1, 2, 3. There's 3 ions there. So I is going to be that. And then Kb is given to us as 1.07 degrees Celsius per mole. There we go. So once you plug all that in, the molality ends up being, because of Celsius leaves, three significant figures, 0.682 mole. And there it is. Okay. Okay, we got through that. So you need to go ahead and study for your test. Make sure you can do these without looking back at the chapter. Have memorized anything you're supposed to take the test. Go ahead and pray very hard. Take your test. Remember to breathe. Take your test. After you take your test, then go online and grade your test with me and with your parent. After you've done that, then go ahead and have your parent sign the top and bring it with you to class next week. Okay. I'm praying you do well on your test. See you soon.